Now, when it comes to integrating the log function, it's not something we do at a 2-unit or a 3-unit level. We will see how we do it in extension 2 integration. So at this stage, all we're looking at really is integrating derivative on function. In other words, going backwards from what we saw yesterday. So if we have an integral and we notice it's in that form, derivative over function, then we know, oh, that must have been a log that we differentiated to get there. And so it would be the log of the function. So this is using a similar idea, I guess, of course. Remember when we looked at the ones where we said, oh, well, if we see it in the form derivative times some function to a power, then we know we can add 1 to the power. So it's the same sort of idea. If we see it as, in this case, derivative is on the top of the fraction, the original function is on the bottom of the fraction, we know it's going to be a log function. So 1 over 7 minus 3x, when you're talking about polynomials, of course, the key is, if you differentiate a polynomial, the order of the polynomial goes down by 1. So if you notice the numerator has an order 1 less than the denominator, then you're looking at a log situation. And so on the bottom, we've got a linear function, which of course has order 1. On the top, I have a constant, which has order 0. So we must be looking at a log function here. Now, the bottom of the fraction is 7 minus 3x. So the derivative of that's not 1, of course. It's minus 3. But we can fix that up. We'll multiply the top of the fraction by minus 3. To balance it out, I'll multiply it by minus a third. And now I've got derivative on the function, so I know that'll integrate to be the log of 7 minus 3x. So again, same idea. We've got a linear function on the bottom. It just says dx on top, but of course that means 1 dx, just like everything else in algebra. We would like 8 on the top of this one. So we could say, well, that's going to be an eighth of 8 on 8x plus 5. And so I know that's an eighth of log 8x plus 5 when I integrate. Order 6 on the bottom, but order 5 on the top. So again, I've got that situation where the top is 1 less than the bottom, so I'm looking at a log function. The derivative of the bottom would be 6x to the power of 5. I've only got 1x to the power of 5, so let's balance that out. We'll make it 6 on the top, but then I'll need to multiply it by 1/6 out the front. And now I've got derivative on the function, so it'll be 1/6 the log x to the 6 minus 2. This is an interesting one, because you've got 1 on 5x. Now we can do this one 2 ways. I could say, well, look, I want to create the derivative on top, so that would be 5, but then I'll need to multiply it by 1/5 out the front to balance it out. So it'll become 1/5 of log 5x, but I could have done this, because remember, we're allowed to factorise, but we only factorise numbers. We can't factorise pronumerals. So I could take the 1/5 out, and the integral then becomes 1 on x, and I have derivative on function, because of course the derivative of x is 1. And so we get our answer, 1/5 log x. Oh, hang on, they're different. Or are they? They are identical whilst you're looking at them, and one says log 5x, the other says log x. Why is it okay? Any clues? No idea? Yeah? Very good. If in the first one we use our log laws, log 5x could be rewritten as log 5 plus log x. Well, log 5 is just a constant. So the difference between the two is, whilst I've just put plus c for a constant, the actual constants would be different constants in the two integrals. So they are actually the same thing. This is where it becomes very fun, I guess, marking this sort of work, because you might not get the answer that I'm expecting, but it may well be correct. And so, of course, I need to check through. Same thing's going to happen when you're doing the exercises. You might not have the same as what the answers say, but that doesn't mean you're wrong. They might have used a log law and got what looks like a different answer, but they are actually equivalent answers. Okay, let's have a look at this one. I don't have the situation we're looking for of derivative on function. I've got 4x plus 1 on the top and 2x plus 1. If you see a situation where the order of the numerator is actually greater than or equal to the order of the denominator, then the first thing you do is a polynomial division. Now, you might not need to do an actual division on something as simple as this, but if you did, you go, all right, well, 2x plus 1 goes into 4x plus 1. We end up with twice with a remainder of minus 1. That means we can rewrite this fraction as 2 minus 1 on 2x plus 1. And now we can integrate, because obviously the constant 2 we can integrate. Our fraction now is in the situation where the order of the numerator is 1 less than the order of the denominator. So we know that's going to be a log function. So we'll end up with 2x minus a half, because of course the derivative of 2x plus 1 is 2. So we'll have a half of log 2x plus 1. So if you see a fraction like that where the numerator has the same order or a bigger order than the denominator, then do a polynomial division and it should fix it up. Should be able to do it then. Let's do a definite integral. So we're going from 1 to 2. Was a bit nice on this one because actually we do have the derivative on top. Derivative of x squared plus 1 is, of course, 2x. I don't need to do anything to this fraction. I know it's just going to become the log of x squared plus 1. Substituting in, we get log 5 minus log 2. Now, with these sorts of answers, if the coefficients of the logs are the same, which in this case they are, then use your log laws to pull it into one number. So I'll get log of 5 over 2. If I had something like, 3 log 5 minus 2 log 2, I probably wouldn't bother. Although you could bring the powers in if you wanted to and still make it 1. So I guess it depends on what the question's asking for. Sometimes they might say, show that it's this, and you've got no choice. But that's generally how I would treat the question. If the coefficients are the same, I'll use my log laws and pull them together. Okay. See, we can't actually integrate x squared log x at the moment because we don't have a product rule for integration like we do for differentiation. And so this is the sort of question where they might say, okay, go and differentiate this. Now go and integrate this. So let's differentiate x cubed log x. So write down the first, diff the second. Well, the second's our log function, so that's 1 on x. Write down the second, log x, diff the first. We get 3x squared. So I have x squared plus 3x squared log x. That now gives me the link to be able to go and integrate, because I now know that when I differentiate x cubed log x, I get x squared plus 3x squared log x. Then logically, if I integrate x squared plus 3x squared log x, I must get x cubed log x. That's not quite what they've asked for, but let's go with it. I now know that when I integrate x squared plus 3x squared log x, I get x cubed log x. That's the answer. They don't want that. So remember, integrals, one of the rules were we could do each term individually if I wanted to. So I've broken that up into 2 integrals, but moved the one I don't want over to the other side. And so I can now say that 3 lots of the integral of x squared log x is x cubed log x minus the integral of x squared dx. Well, let's perform that. Integrate x squared, I get x cubed on 3, but then dividing both sides by 3 as well, I come up with the answer. There's my integral of x squared log x. So when you see that sort of question where it says differentiate, hence integrate, if you don't get something that looks like what they're asking you to, hence integrate, you've probably done something wrong, because you are expecting some sort of link there. So watch out for that. Okay, so a couple of questions on exercise 12D, which will probably just be straight integrals. E is probably the applications where we'll go and find areas and volumes. But just a note on areas and volumes before I begin, or end, because I've already begun, haven't I? Remember we said you can't find the log of a negative number. Now, if you have a look at our basic hyperbola over there, if I said find the area from, say, I don't know, -4 to -2. Now, clearly it has an area. If you integrate 1 on x, you get log x. But if you sub in -4 and -2, you're now finding the log of a negative number. We have a problem. The reality is, whilst I've said to you that when you integrate 1 on x, you actually get the log, the true integral is this. The integral of, say, dx on x is not the log of x, but the log of the absolute value of x. Okay? So that way, if we have to substitute negative numbers in, we don't have a problem. And the reason you'll see a lot of them don't bother with it, I mean, here's a copy over here of our standard integral sheets that you get in the HSC. They've got integral of 1 on x dx is just log x. They don't put the absolute value signs around. Mind you, they make a note where x is greater than 0 on that one. The reason that's not an issue, if you integrate, sort of say, what did I say, -4 to -2, did I say? Something like that. Oops. Okay, so if I didn't worry about the absolute value signs, look what happens. I get log of -2 would be first, minus log of -4, which of course is a ridiculous statement, because you can't find the log of -2 and you can't find the log of -4. However, if you use your log laws, it then becomes the log of -2 over -4. You now got a positive number and you can find that value. But you can't, because if you went from -1 to 1, you'd be crossing the discontinuity. And so therefore, theoretically, the area is infinite, because along that y-axis, you'd have an infinite amount of area. So you never get that problem. Okay? So technically, it's the absolute value of x, but don't worry, you're not going to get penalised if you just write log x rather than the absolute value of x. But keep that in mind if you do get a situation where you have to substitute in